Hello, my name is Che, and I'm honored to present our paper, Learning with Noisy Labels by Efficient Transition Matrix Estimation to Combat Label Miscorrection. This is the joint work by 성민계, Che, and Chunyoung-lee with the corresponding author Buru Zhang from HyperConnect, the subsidiary of Match Group and Tinder. We first skimmed through the preliminaries to understand our paper, such as the task definition and related works. Then we go through the ideas of our method, and finally we briefly show the experimental results and analysis. First of all, our paper concentrates on the task of learning with noisy labels. The recent success of supervised learning is fueled by the annotations of humans. Hence, it is somewhat natural to assume the mistakes of humans, that is, label noise. To combat the label noise, we can split the labelings into two. First, a data set with relatively noisy samples, hence cheap to label, and second, a smaller data set but with much cleaner labels from the annotation experts. It is empirically known that having a small clean set benefits the performance greatly while having an additional but negligible labeling cost. Among various noises, we concentrate on the class-dependent label noise. Let's say we are building a classifier that classifies cats, dogs, and cars. Obviously, the annotators would be more confused between cats and dogs compared to cats and cars. The label transition matrix captures the relationship between classes. Note that we can estimate the matrix by using both noisy and clean datasets. By attaching the label transition matrix to the classifier while training with noisy labels, we can yield a statistically consistent classifier. This can be intuitively understood as being skeptical towards all the labels, weighting the level of skepticalness with the label transition matrix. There have been many approaches to solve the noisy label problem, but model-agnostic meta-learning or mammal-based label correction methods are gaining traction. The basic idea is it is correcting the labels with the model predictions, effectively reducing the level of label noise. However, there are two limitations. First, after correcting the labels, the model blindly trusts its correction. Hence, wrongly corrected labels will be kept throughout the training, causing the model to sustain its mistakes. Also, Mammal is inherently slow in training because it requires virtual updates with inner optimization loops. Our method aims to elevate these issues by efficiently estimating a transition matrix to learn with noisy labels while continuously correcting the matrix on the fly. Basically, our method is correcting the labels, but remains skeptical about its correction by using the transition matrix while training. However, if the model is continuously correcting the labels, then the transition matrix keeps changing throughout the training. Hence, it is essential to efficiently estimate the transition matrix while training. That is why we adopt a two-head architecture that consists of two classifiers, a noisy and a clean classifier with a shared feature extractor. Experimental results indicate that our method's performance is superior in both accuracy, the upper the better, and training efficiency, the leftmost the better. It further shows superior accuracy on the large-scale clothing 1M dataset, which contains real-world noise. Finally, we finish the presentation by going through the analysis. We conduct various theoretical and empirical analysis in the paper, comparing our FASN with other methods, such as is our method correcting the labels accurately compared to others? Or what happens if it's miscorrected? Is our method robust to its mistakes? Or is the estimated transition matrix accurate? Or what is the theoretical upper bound of the transition matrix estimation? Thank you for listening to the presentation, and fasten your seatbelt for blazingly fast learning with noisy labels.